All right. Let's look at the history of deep learning. So basically, deep learning, neural network, and multi-layer perceptron mean the same thing. Yeah? It all started in 1957 when Frank Rosenblatt invented the perceptron. And the perceptron is a binary linear classifier. And we've looked into the perceptron in session 5 of this course, but I just want to show you again how this works. It's quite simple. You have inputs x0, x1, x2, and these inputs are given weights, w0, w1, w2. And then what you're going to do is add them all up. You're going to aggregate these three signals. The weights are there to signal the importance of the input. Yeah? So if x2 doesn't have a lot of importance, your w2 will be small. So here is the summation, the aggregator, and there you have x0, w0 plus x1, w1 plus x2, w2. This is your aggregated signal. Yeah? And if this aggregated signal is larger than a value b, and b is a threshold, this is this symbol here, then the neuron will fire. Neuron will fire. Okay? It's a bit similar like a brain where the nodes here are neurons. Yeah, although it's not proven. Yeah, but it's a bit, the intuition is a bit similar. So when the neuron fires, the output will be 1. Yeah? For example, if you want the output to be 0 and 1, if the neuron fires, it's 1. If the neuron does not fire, it's a 0. Yeah? So this all created a big hype. Yeah? But then came 1969. Yeah? 1969 was a great year. If you believe Bryan Adams, the summer of '69, I wasn't born yet, so I don't know if it was really a great year. But what happened in '69 is people went to the moon, and the Belgian cyclist Eddy Merckx won his first of 5 Tour de France. So definitely a special year, 50 years ago. It was not such a good year for Rosenblatt, because Paper and Minsky wrote a book where they highlighted the limitations of the perceptron. So here they say perceptron has limitations. Yeah? And the most popular limitation is that the perceptron cannot solve the XOR problem. So a XOR port is something from electronics, from electronic circuits, and it's actually very simple. You have 2 inputs and an output, and the XOR, which is an exclusive OR port, will give 0 when the x1 and x2 are the same, and it will give a 1 when they are different. That's the definition of XOR port. So the zeros here are this one, and the 2 crosses are the 2 middle ones. Yeah? Now try to separate these 4 points by a straight line, which is basically what a perceptron is. It's impossible. You cannot split the circles from the crosses with a simple line. Yeah? For example, a perceptron can also not solve this, where you have the positive class in the circle and a negative class outside of the circle. Yeah? Perceptron cannot solve this. So, 2 things happened. It was the start of the first AI winter, AI winter number 1. Yeah? And what became clear is that there was a need for nonlinearity. Okay? So, what happened next, and we're at the end of the 80s. In 86, Hinton actually solved the XOR problem, and he showed that backpropagation works. If you don't know what backpropagation is, don't worry, we will see what it is, but it's the key algorithm in neural networks. Yeah? Then we have, 3 years later, Jan LeCun. He basically built a CovNet, a convolutional neural network, and he had the CovNet to read handwritten digits. This, of course, was adopted by the US Postal Service to read zip codes on handwritten addresses on envelopes. And it worked quite well. Yeah? But despite all these good things happening, there was a second AI winter. Yeah? So let me put AI winter number 2. That actually spans the 90s and the first half of the 2000s. Why the AI winter? Well, it's not an AI winter per se, it's more of a deep learning winter, because progress was made on the shallow learning front. In the 90s, you had a support vector machine hype that, triggered everybody to focus on support vector machines and kernel methods. Why were these so popular? Well, a support vector machine supports nonlinear boundaries. Yeah? So if the data is not separable in 2 dimensions like here, what you do is you project the data to higher dimension. So, and you leave these 2 zeros at the bottom, and you create a 3rd dimension where you put the 2 crosses. Yeah. So we had a kernel trick: project the high dimensions, separate the data at the high dimension, and then bring everything back to the 2D or 3D dimensions. Yeah. So what happened? Well, there was not a lot of funding going into deep learning. That's one thing. It was very hard to get papers approved at conferences, just because SVMs were so popular. So I will write SVM here. So SVM and the kernel trick, which we have discussed in a previous session. Now, what has changed? Well, suddenly in 2006, Jeff Hinton, he rebranded neural network multi-layer perceptron to deep learning. He called this deep learning. And by calling this deep learning, all the other learning techniques, including SVMs, suddenly became shallow learning. And intuitively, deep learning sounds much more interesting. It makes you feel, oh, it's deep, it's good, it's accurate, right? So this is a brilliant marketing move here, where you rebrand the technique. And the second thing that brought neural nets back on the map was the development of GPUs. GPUs are the graphical processing units that were actually developed to support the gaming industry, to support these high-resolution games. Because here, another reason why there was a second AI winter for deep learning specifically is because neural networks were still difficult to train because of the processing capacity. Yeah? But this changed with the GPUs. So between 2006 and 2019, there's a massive amount of funding going into AI and deep learning. And for example, today, if you want to do computer vision or natural language processing, nobody would think of doing it the other way than the deep learning way. Yeah? So between 2006 and 2019, everything got bigger, better, and faster. Alright, so far for the history.